All right, welcome back to the channel. Today we're going to be talking about infinite series, and just to make sure everybody understands what the ideas are, because we have a varied audience of people watching these videos, I just put up 4 different series, and just to motivate the idea of adding up an infinite number of numbers, which most people will just say, well, if you add up an infinite number of numbers, that should give you infinity. And most of the time that's actually true. Maybe I shouldn't say most of the time, but often that's the case, but not always. So for instance, if I look at the first series here, 1 plus 2 plus 3 plus 4 plus 5 and on and on and on, I know that's going to go to infinity. So we usually call that divergent, okay? Because we're not really that interested in series add up to infinity. The next one, 1 plus a half plus a third plus a fourth plus a fifth plus so on, so on. Some of you may know this as the harmonic series, and we can prove this actually is equal to infinity. That will not converge. It will not settle to some fixed value. The next one, 1 plus a half plus a quarter plus an eighth plus a 16th. Well, that's geometric, and a lot of us have study that in high school, and definitely that will sum. That's 1 plus a half plus a quarter. Does anybody know what it is? Well, it's actually 1 plus 1, which is 2. There's a 1 here. So if I were to take a half plus a quarter plus an eighth plus a 16th to infinity, all of that would be equal to 1, and then 1 plus the initial 1 would give me 2. So again, this is that counterintuition. How on earth could, when you add an infinite number of numbers, give you a finite value? Well, it actually is true. Gets into the ideas of limits. This next one, 1 plus a quarter plus a ninth plus a 16th plus a 1 over 25. Well, this is actually called a p-series. A p-series where, in fact, the denominator here, compare the p-series here to the harmonic. Harmonic is p-series as well. But you'll look at the denominators 2, 3, 4, 5 and compare them to 4, 9, 16, 25. These denominators are getting bigger faster. And so, not to get into p-series in this video, but this one will actually converge. This one will actually add up to a number, and that number, in fact, is actually pi squared over 6 rather. We're not going to show that in this video. Maybe I'll do a video on that, but just to get into the idea that generally when you're given questions and you're asked to talk a little bit about infinite series, it's usually, do they converge? Do they level off to a finite value, or do they diverge to infinity? Okay, so let's take a look at the questions that I put up here for today. We'll even come back to some of what we just talked about to be able to address the question, do these series that are on the board here, do they converge or do they diverge to infinity? Well, if you look at the first one, notice that it looks very similar to geometric. Like if I look at that portion right there, that looks an awful lot like 1 over 2 to the k. Adding that up, I'll use the sigma symbol. That's a fancy sigma. And that's the same thing as sigma, 1 over 2 all to the k. I'm just relaxing my upper and lower limits of summation there. And that's geometric, right? Because if I was to expand that out, that's going to give me a half, right? If I go from k1 all the way to infinity to 1 over 4 plus 1 over 8 plus 1 over 16 plus ... That's just going to continue on and go on and on and on. And this actually, as we already talked about, equals 1. And you can show that. There's more complicated ways to show that using partial sums. Or a simple way is to use simply the area of a square. So the area of a square, let's say the side lengths are 1 by 1. Then I could think of each of these terms as representing the area, the partial area of this square. So a half means half. So there's half of the area. And then there's a quarter more. So let's add in a quarter more. and there's an eighth, and there's an eighth. And of course, as I continue to do this to infinity, it's going to cover the entire area to the limit. So what we can say is, since the area of the square is 1, then this series should sum to 1, and it will. Some of you may remember too from high school that since it's geometric, right, where the first term is a half and the common ratio is a half, you can use the formula, the first term divided by 1 minus the common ratio. And the common ratio here is a half, the first term is a half, so a half divided by 1 minus a half is 1, and you could get it that way too. So now I'm raising this because this is actually very useful, because look at the two questions we have. Again, they look like they're geometric, except in this denominator, you'll notice that I've got a plus 3. And in this denominator here, I've got a minus 1. And so in this case, if I know that 1 over 2 to the k is convergent to 1, then just my intuition tells me that if I add 3 to the denominator, even though it's not geometric and I can't use the geometric formulas, my intuition tells me that the denominator here are going to be larger. So if 1 over 2 to the k, 1 over 2 to the k converges to 1, then 1 over 2 to the k plus 3 should also converge to something less than 1. Now maybe I can't come up with the actual sum to infinity, but maybe I can verify or show how that's true, how it is convergent. So again, the intuition tells us that it's convergent, so how do we demonstrate it? Well, if I look at 2 to the k plus 3, and I compare that to 2 to the k. Well, I know that 2 to the k plus 3 is going to be greater than 2 to the k. And if I took the reciprocals of both of those, so 1 over 2 to the k plus 3, and I compare it to 1 over 2 to the k, then I'm going to flip my inequality symbol. Okay, this is for values of k belonging to the positive set of integers, right? So we're looking at where k goes from 1 to infinity, and we're looking at integer values. Well, we've sort of determined it here, because notice, if 1 over 2 to the k is greater than 1 over 2 to the k plus 3, and we know that 1 over 2 to the k, those values, if you add them up, converge, then just by comparison, then this much must converge. And so this is the basic comparison test, comparing your question to another known series that you know converges. So in this case, your teacher might want you to simply say, the series converges, I'm just going to shorthand it, by comparison. By comparison. Just a simple direct comparison. Now, look at this one here. This is very similar, except it's difficult because the denominator is minus 1. Then if I were to compare 1 over 2k minus 1 to 1 over 2 to the k, well, now you can see that this series that we have is actually bigger than the known geometric. And so that limits the use of the comparison, the direct comparison. So we can use another way, actually. It's called the limit comparison. So what we do is I'll tell you what the limit comparison test is. We take the limit of two sequences, the ratio. So if I've got a sequence an and a sequence bn, and I take the limit of that as n goes to infinity, if this limit is greater than 0, then I can make a conclusion. If one of those sequences is in fact convergent, so is the other one. And also too, if one of them is divergent, so is the other one. So they work together. If one's convergent, so is the other, and divergent, so is the other. That requires that the limit of this ratio is greater than 0. So what I'm going to do is take my problem, and I'm going to let the an be the question that I'm given. Say this is on my test, and I want to show a good answer, right? And then I'm going to use the second sequence as your known sequence. You know that the geometric is convergent. So let that be your comparison, but we're going to use a limit comparison, not just a simple comparison. What the limit comparison test says is take the ratio of those. So if I take this divided by this, well, that's going to give me 2 to the k over 2 to the k minus 1. That's the ratio of an over bn. And if I was to take the limit of this as k approaches infinity, then I could divide the top and the bottom by 2 to the k, do you see? So what that's going to give me is the limit of 1 over 1 minus 1 over 2 to the k as k approaches infinity. And I'm assuming that you know some basic limits. So if I was to take the limit of this, do you see that this here is going to go to 0? And the answer to that is 1. So come back to the criteria. We've just found the limit of the ratio of those two sequences or series. We're really talking about series. And we found that it's actually greater than 0. So the conclusion here is that since Bn converges, we know that if we were to think of Bn as a series, then that means that the series An also converges. So our conclusion here, therefore, we would say it's convergent by the limit comparison test. And just pay attention to what your teacher is asking you to show or to say in your conclusions. They're training you maybe for an IB exam or for an AP exam. So just be careful about your language. So there's a little bit of a toe in the water today on infinite series and using comparison. Usually the geometric series, especially for high school and first year university, is a really good one to use for comparison purposes. P series too, if you're studying any of this. And also the use of the limit comparison test when a direct comparison is difficult to set up. All right, if you like this video today, don't forget to slap a like on it. Don't forget to subscribe if you haven't already, and I'll see you right back here in the next video.